Hello everybody, welcome to the second video for chapter 34. In this video we continue this section where we introduced Snell's Law, and we'll talk about a phenomenon called total internal reflection, and we'll also go on to the next section talking about image formation from refraction. Okay, let's get started. So this problem right here hints at what's going on. So we have a light ray that's making an angle 30 degrees with respect to the interface. And the question posed is, will any light escape? So we're starting off in the glass medium, and we're wondering if any light can leak out into the air. So we'll see why that might not be possible when we look at total internal reflection. Okay, so when we talked about Snell's Law, we talked about a light ray starting in air and then going into water. And remember that the light bends towards the normal. If you're going from the lower index of refraction material to the higher index of refraction material. So in total internal reflection, though, we're going to start in the higher index of refraction material. So I'll call this N high and N low. Okay, so this phenomenon only occurs if you start with a light ray in the higher index of refraction material. So let's see what goes on. So I'm going to imagine light that always strikes right here. So this is the normal direction. If you have light that is on this path, so if you're starting in the higher index of refraction material and you're going towards the lower one, the light will refract away from the normal. So the outgoing light ray might look something like this for that first light ray. And to show different light rays, I suppose I'll use different colors here. So what happens if we have a greater angle of incidence? Remember, the angle of incidence is measured relative to the normal, so that's a greater angle. So again, we're bending away from the normal, so it'll look something like that. All right, so there's actually a limit to what goes on here. So there's some maximum angle of incidence where the light that comes out is basically 90 degrees. So there's a light ray that, if it makes it through, it'll come out just barely 90 degrees. And so that critical angle is called just that. So this one where the outgoing light ray is 90 degrees, that light ray is called the critical, so that angle of incidence is called the critical angle. And any light that comes in at an angle bigger than that angle won't be able to escape. It'll be impossible to satisfy Snell's law. All right? So this critical angle is defined such that, so we're going to write down Snell's law. So starting in the higher index of refraction material. So N high times sine of this critical angle is N low times sine of the lower, the outgoing refracted angle. And by definition, we're going to say, well, the biggest that can be is 90 degrees. Okay, so in this formula, so sine 90 degrees is 1. So we can solve this formula for the critical angle. The critical angle is the arc sine of N low over N high. So this is a phenomenon where you have to start, it only occurs if you're starting in the higher index of refraction material. And so it makes sense to take the arc sine. So this fraction is guaranteed to be less than 1, if that's true. So low over high. So you can take an arc sine of a number less than 1. You can't take the arc sine of a number greater than 1 because there is no angle for which, sine of the angle is greater than 1. Okay, and notice how this is exactly what your book has right here. I kind of don't like the way your book has it because then you have to remember, well, what's 1 versus 2? So I like writing it as N low over N high, and it's understood you have to start off in the higher index of refraction material. So I think it's a little more, it's saying a little bit more about what's going on with the words. Okay, so the main statement here, so with that critical angle, any light with angle of incidence greater than the critical angle it can't go through. So Snell's law can't be satisfied. There's no angle of refraction that will satisfy Snell's law, and as a result, all of the light is reflected. So if you shine laser light, you can see this. As you get higher and higher angles right here, you can see the light escape. But then you start shining light this way, all of it is reflected. You can't see any light that gets through. So any light with an angle of incidence bigger than the critical angle will be quote unquote totally internally reflected, or it will undergo total internal reflection. Reflected. Adjective versus noun. Okay, so we can look at this problem from before. Okay, so there's two ways that we can look at this problem right here. So I'll call this the original problem. So first of all, we can assume that the light will escape and try to just use Snell's law and figure out what happens. And then we can also just compute the critical angle and then see if our angle of incidence is bigger than the critical angle or not. So there's two ways that you could approach this problem. Okay, so I'll say original problem, two different solutions. So I want to analyze it two different ways. The first way, okay, so we're just going to plug this into Snell's law. So remember the incoming angle. So we have n glass is 1.50 and n air is 1.00. So our angle of incidence, remember that the labeled angle in the problem was the angle with respect to the interface. So again, as a warning, you have to define your angles with respect to the normal. So if I'm going to use Snell's law, and I need to have this angle right here. So that'll be the complement of 30 degrees, which is 60 degrees. Okay, so let's try Snell's law. So this solution will just, let's say we didn't know anything about total internal reflection. We're just blindly going through Snell's law. So let's see what happens. So we have n glass times sine of 60 degrees is equal to n air times sine of theta refracted. And we want to solve for theta refracted. We want to see what angle with respect to the normal the light emerges in air. So this is air. Okay, so plugging in numbers here. So it looks like theta, sine of theta r is equal to n glass times sine of 60 degrees. So let's see, 1.5 times sine of 60 degrees divided by n air is 1.00. And that's 1.30. So sine of our theta refracted is 1.30. So we need an angle where when you take the sine of it, you get 1.30. Well, that's impossible. Sine of any angle is between -1 and 1. So this is impossible. So this is one indication that that no light can get through. It would be impossible to satisfy Snell's law. Okay, so our conclusion here is that no light gets through. Okay, so that's one way of seeing how this works out. Another solution is to compute the critical angle and then see if your angle is bigger than the critical angle. So we already suspect, based on our solution for part A, we suspect that our angle of incidence 60 degrees is bigger than our critical angle. But let's go ahead and verify that. So let's calculate the critical angle. Theta c is arc sine of n low over n high. So remember, we're starting off in the higher index of refraction material. We're starting off in glass and we're going to air. So total internal reflection is possible. So if we take arc sine of 2/3, we get an angle of 41.8 degrees. So then we infer that we will have total internal reflection for this setup. So since our angle of incidence, which is 60 degrees, is greater than the critical angle, we have total internal reflection. Sometimes you'll see this abbreviation, TIR. total internal reflection. Okay, two different solutions, same conclusion. No light will go through to the air. So this is an important phenomenon for fiber optic cables. So you have transmission of information through light, through E&M signals, and you don't want any of that light to leak out of your cable. You want whatever signal you send to be received. So you want no light to leak out. And so you have these cables. You want the light to stay in, and so you want your light ray to maybe go like this, and then you want all of it to bounce off this way. You want all of that to bounce off this way. So you want to make sure that it stays your light ray is roughly parallel to the interface. So it doesn't have to be perfectly parallel. It just has to be bigger than the critical angle. So every time it bounces off, it has to be bigger. This angle of incidence has to be bigger than the critical angle to stay in. So I'll just say that this is relevant for fiber optic cables. So your light that you're sending from the light that you're sending over long distances had better be in something with a high index of refraction relative to the surroundings. The bigger the difference in the n values, the smaller the critical angle, and so the more likely that your light will just be totally internally reflected. Okay. Okay. And your book goes over that this is one of the main applications of this as well. So you talk about core and cladding. So that's the signal is traveling in the core and it's surrounded by some cladding, and you want to make sure that the difference between them is as big as possible. Okay. Now we're about to we're getting into lenses, and lenses work because of refraction. So this is sort of a warm-up section to lenses. So the example that they talk about, so maybe I'll just zoom in and explain. So let's focus first on this picture, and then we'll go backwards. So look at the object P on the far left of this image. Okay, so an object is in water. The solid blue light rays are emerging from that object, and then once they travel from N1 to N2, so from water into air, the light rays bend away from the normal. Remember, you're going from a higher index of refraction material to a lower one, so you bend away from the normal. Now, if you're a person over here on this side, so I'm imagining looking at my object from the air. I can't write on this, by the way, so I'm writing it over here. Now, if I look at these light rays, these solid blue lines that emerged, they look like they came from this point P prime. So notice how your book traces back. So these dotted, these dotted lines right there are traced back to a point P prime. So you see an image. So the object is far away from the interface, but you see an image closer to the interface. Okay, because it looks like, so your brain is used to just whatever light that you receive. Your brain is used to tracing it back and seeing, well, I'm used to it. So the reason it looks like that is because the light emerged from what looks like this location, a certain location. So we call that an image. And remember, last video we introduced the notion of a virtual image. So the fact that light doesn't actually come from the point P prime means that that's a virtual image and not a real image. So we haven't yet seen an example of a real image, but this is another virtual image example. Last video we said that when you look at yourself in a mirror, that's also a virtual image. So this happens because of the refraction at that interface. That's why the apparent path is different from the actual path of the light ray. As a result, if you have an object in water and you look at it, it looks like the object is shallower. So I'm imagining now looking down. So imagine you're looking into a pool or a lake or something and you see a fish. The fish is going to look like it's shallower, at a shallower depth than where it actually is because of this phenomenon. Okay, so your book proves where that image is. Now, in this proof, your book uses the small angle approximation. So it's small angles with respect to the normal. We're going to assume that we're looking at an image pretty close to the normal. Okay, so that's what I mean by looking, you're going to look straight down at a lake or a pool or whatever, and you're pretty close to the normal. You don't have to be exactly right on the normal, but pretty close. You can't be looking at a big angle relative to the normal. So as long as that's true, you can prove, and your book does this, that you can show this relationship between the apparent depth and the actual depth of the object. Okay, so I'll say that, so this right here, I'm going to ignore the minus sign in this video. We're going to have strict rules for what that minus, for what's plus and what's minus when it comes to images. But I want to stick with lenses when we introduce those rules, so that's why I don't want to worry about it right now. So I'll just say that S is the object distance, object depth. And so you have some light that, light that goes straight towards the interface is just going to go straight out, right? 0, for Snell's law, 0 equals 0, so that's fine. Then this light ray is going to be bent away from the normal, and we're going to have to trace this back. And then similar for the light ray on this side. So I showed sort of an extreme, I showed a big angle of refraction relative to the incident angle. So this distance right here, where those light rays trace back, that's the apparent depth. So I'm going to stick absolute value signs on here, just because I'm just focusing on the distance. I'm not focusing on whether it's positive or negative. Okay, so now notice I assumed here that S prime was less than S. And that happens if if we started in the higher index of refraction, and went to the low one. Okay. If we swap these, then the apparent depth would be deeper. It would be bigger than the actual depth. Okay. So I'm going to write right here. So the ratio of the n values is the ratio of the depths. So the lower one over the higher one. Well, maybe I'll just do N1 and N2. So it looks like, N2, so I'm drawing this so that N2 is less than N1. But the formula I'm going to write down actually isn't going to assume that. So N2 divided by N1 in this picture, that's a number less than 1. And this is equal to S prime, the magnitude over S. So for water and air, water N2 would be 1.00, and N1 would be 1.33. So that fraction is about 3/4. So this picture right here is not 3/4, right? That's closer to 1/4. But for water, it looks like images are, so the image of something, it's at a depth that's only 3/4 of the actual depth. Right? So if you're looking into a pond from above, you see a fish that looks like it's 1 foot under the water. It's actually 1.33 feet under the water. So whatever depth it looks like it's at, it's actually 1.33 times that. So maybe I'll label this as apparent depth. But the actual name of this title of this section is Image Formation by Refraction at a Plane Surface. So we're going to complicate this in future videos by talking about lenses where the interface is going to be curved. So the geometry can get pretty complicated there, but we're just going to look at some main results. Here you just have to know that, so if it's just a flat interface, so notice how it's just one straight line right there, the depth can change, the apparent depth can change, and the ratio of the n values gives you the ratio of the depths. And you can convince yourself with a ray diagram of which way, which way this fraction needs to go. What number needs to go on the numerator versus the denominator there. Okay, so you might notice this when so one common example is a toilet bowl, If you look at, so if you're used to, for example, a toilet bowl where the water is filled up all the way, you're used to the toilet bowl looking like it's a certain depth. And then if you ever see a toilet bowl where the water isn't in, it looks a lot deeper. Looks 1.33 times deeper than what you're used to. And the reason for that is the water makes it look like it's not as deep as it actually is. So that's probably the most common example where you can see the difference right away. But I'm sure other non-potty examples exist. Okay, so next video we'll focus more on lenses. So this is refraction and images formed by refraction, but more complicated interface shapes.